So let's start from where we left off. So this is the J2 plasticity model, which pertains to just the plastic element, the dry friction element equivalent in 3 dimensions, right?
Yes, sir.
And if we add a spring, it will become elastoplastic. How do I do that? In the very same way that I did earlier in 1 dimensions, we will do it in 2 dimensions. That there are 2 elements to it, the elastic element and the plastic element. The plastic element will pertain to plastic strain, and the elastic element will pertain to elastic. And therefore, kinematics will now can be represented as epsilon dot is equal to epsilon dot E elastic plus epsilon dot. But during rigid flow, during plastic flow, we recognize that from flow rules that the plastic strain is incompressible. That can be written as one of the constraint equations. And then there is this elastic range where yield condition will come into picture. We test whether the yield condition is satisfied. And if yield condition is not satisfied, then I can have the elastic response given by C times epsilon plastic. I can write this as sigma
epsilon
dot,
elastic, right?
Epsilon elastic. Sorry. I can also write this as sigma dot is equal to C times epsilon dot. That's all is the difference. Beyond that, everything remains the same. Of course, I use flow rule. This is one way of representation that we used. If you notice, F was equal to tau dot tau. And therefore, if I differentiate with respect to tau, I'll get a tau, which is nothing but this. But it also tells me that if F is something like a potential, the flow is occurring along the gradient of the potential. Does this strike a bell? In fluid flow, you would have drawn the flow net, if you remember. You would
Yes, sir.
have
Yes, sir.
the potential lines
and flow lines.
and the flow lines.
Flow lines.
Right?
Yes, sir.
They are perpendicular to each other.
Yes, sir.
How do I represent a perpendicular normal to a particular surface? I take the gradient of the surface.
Yeah. Yes, sir.
That's exactly what it is. Just to show you that that is nothing but flow rule, that the flow is occurring normal to it. Okay?
Okay, sir.
We also call
Sir.
the flow rule as normality rule. The question is, are there rules which need not satisfy this? The answer is yes and no. Sometimes people in granular flow define 2 different conditions. One condition as potential function, the other as the yield condition. Okay? I don't want to confuse you now. So if this is clear, we'll move on and then come back to that. The flow lines and the potential lines. The flow and the potential lines are perpendicular to each other. Then the Kuhn-Tucker condition is the same condition that we used earlier. And that's it, over. We have elastoplastic model where we have epsilon, epsilon p and sigma. Now earlier there was only epsilon and sigma. Now we have epsilon p because epsilon p is different from epsilon. And the elastic response is given by this. This is for the total stress. This is for the shear stress alone. In elastic models, it is 2 mu times gamma plus lambda times E. This lambda times E is what is given over here. P is equal to 3K times E.
Okay. Yes.
And then the other things are the same. Flow rule represented by this, and Kuhn-Tucker conditions as phi times F is equal to 0. That phi is always non-negative and F is always equal to or less than 0. Ultimately, all these should give us one single relationship. What is that relationship?
In rigid plasticity means once we reaching to the yield, till then it is means behaving
No
rigid till
deformation.
it reaches to, yes sir, no deformation. But in this case there will be elastic deformation till it reaching to the yield limit,
Correct.
right?
Correct.
So
That's your essential difference.
yeah, so till that there will be some deformation, I mean volume change will be there, but after that it will start flowing and there will be no volume change, right?
That's correct. That is why if you look at this E
Yes sir.
times 3K is equal to pressure is written. You don't have any
Yes sir.
plastic strain coming into picture in this. You can see
Yes
that?
sir. Yes sir.
So we can either supply stress and try to find strain
Strain.
and or vice versa.
Exactly. So either I supply strain and find out stress, or supply stress and find out
Or
strain.
find out strain. Yes sir.
Or in other words, I'm trying to find the relationship between stress and strain. Is it not?
Yes, sir.
Yes sir.
That's all I want to find out. If that is the
So
case, yeah.
In third case there is written a capital C, right?
Capital
C. Capital C. Capital C.
Yeah,
Sigma is
that's
equal
the,
to C into epsilon E.
yeah.
So what is the dimension of that C?
So this is going to be
Fourth dimension.
if you have stress as 9 quantities, strain as 9 quantities, this will be a 9 by 9.
9 cross 9, yeah. 81 quantity.
On the other
Fourth
hand, if
dimension.
this is 6 of them, this is 6 of them, this will be a 6 by 6 matrix.
Yes, sir.
Okay sir.
Okay.
Yes sir. Sure.
So in reality, I just want to find out this relation between sigma and epsilon. The question is, instead of writing all this, can I reduce and write in a single form? That's the question. Okay. So let's see if we can do that. So what we are aiming at is, given the increment in strain, what is the increment in stress? Correct?
Okay sir. Yes sir.
Yes, sir.
Notice here, I've used 4 dummy variables here.
Okay.
2 of them are dummy variables, the other are
Yes sir. Yes, sir.
ij
3 variables.
repeated over here. So it is summation of k and l. You have 9 equations that you can generate here. Correct?
Yeah. Yes sir. Summed over to K and L.
Right. We also know that C is equal to epsilon dot minus epsilon dot P, which is nothing but 5 times tau.
Tau. Yes sir.
Correct? 5 is
Yes,
a
sir.
rate. And also, if I differentiate from the consistency condition, if I differentiate, I know F is a function of sigma, correct?
Yes, sir.
Yes sir.
So F dot is nothing but dou F by dou sigma times sigma dot.
Yes sir.
During plastic deformation, that's equal to 0. Right? Right?
Okay.
Yes sir.
And therefore, I'll get phi to be equal to tau dot epsilon dot divided by k square. Now it's a matter of just substitution over here. So I'll get tau dot epsilon times tau. So it will be tau times tau dot epsilon by k square. Correct? And that can be written as A dyadic B times C.
C.
What is A dyadic B? Any of you know?
No, sir.
Yes sir. We have gone through that.
If you don't
Not
know,
remember
don't
right
worry
now.
about this. Just take it as A times B transpose.
Yes sir.
Okay, sir.
A is nothing but tau,
Yes sir.
which is 9 quantities. Yeah?
Yes sir.
Tau transpose is 9 quantities. So if you have 9 times 9 column times row, you'll get a 9 by 9 matrix.
Okay.
And therefore, now I can write sigma dot is equal to C times epsilon dot, which is nothing but I times epsilon dot
Epsilon.
minus this quantity, which is 1 by k squared times tau dyadic tau. Now, if you look at it carefully, this entire quantity is nothing but k, and that k is the tangent modulus.
Sure.
So once I know it is plastic flow, then I can directly use this relation.
Sir, one question, sir.
Yeah.
Sir, what is the physical representation of this tangent modulus?
What is the what?
Physical representation of this tangent modulus.
Physical representation of tangent modulus. 1 second. No? Let me just open this. Stop the share, or I can directly do this way. You will be able to see. You will be able to see the camera also.
Yes, sir.
Yes, sir.
So it's very small.
But in a very small way.
It's very small. Okay, let me stop sharing this. Now it's okay.
Now it's fine. Yeah, fine.
Okay, so in one dimension, if I have, let's say, sigma versus epsilon, let's say it's like this. At any point, the tangent is the modulus. In the elastic region, it is nothing but elastic modulus. Here it is tangent modulus. Got it?
Yes, sir.
That's it. Everything else is the same.
Can you show this, sir? I'm not able to see the.
You're able to see the screen?
Others actually have to mute their voices. Actually, that's why.
Yes, sir. If they mute, then we'll all be able to see.
Yeah, they are all seeing. You have to mute yours.
Rambabu, can you mute your? Can you mute your one? Yeah.
Yeah. Pragyan also, so that you can see. So this is the tangent modulus. For elastic condition, it is nothing but the elastic modulus. Okay. The other definition that they give is what is called secant modulus. Let us say it is like this. For this point, if I have to find out secant modulus, I just join this with the, and this is secant modulus. But what is important for us is the tangent modulus. So far, okay?
Okay, sir.
Yes, sir.
The tangent modulus changes the plot, right?
Tangent modulus signifies nothing but the relationship between the increment in stress to increment in strain. Is it not?
Yes, sir.
Oh, so it's instantaneous stress working.
Yeah, you can call it as instantaneous increment in stress to instantaneous increment in strain. The relationship between these two is called the tangent modulus. If I had taken sigma and epsilon over here, I would have gotten secant modulus.
Yes, sir. Yes, sir.
Got it?
Yes, sir.
Let me proceed. In a matrix form, it will look like this. This is the elastic part of it. And therefore, this whole thing times unit matrix minus 1 by k square times this tau matrix times the transpose of this tau matrix times epsilon dot matrix will give me sigma dot over. Got it?
Yes, sir. Yes, sir.
So I can also have partially stress, partially strain form of loading. It's there in the notes that I have given. Supposing I have something like this, how do I proceed? Let's say given sigma epsilon t, and we need to find out sigma dot and epsilon dot. This f of t is given to us. How do we proceed? First thing that we do is to find out whether the yield condition is met. Listen to me carefully,
Sir?
because you may have to write the code related to this. After that, see if you can get, by guessing it to be an elastic response. That is, assume phi is equal to 0. Then what will happen? K is nothing but C. If K is nothing but C, now I can put it down here and get what is epsilon dot. Is it not? Are you people with me?
Yes, sir.
Yes, sir.
So that I can find out sigma dot to be nothing but C times epsilon dot. This is clear to you, no? This is just using this equation to find out and remove epsilon dot altogether.
Yes, sir.
If the guess is right, no problem. But if the guess is wrong, then plastic flow occurs and we calculate like what we have shown earlier, the previous slide. Instead of C, we use kappa. That is all. Okay?
Yes, sir.
Often it is possible to non-dimensionalize this plasticity model so that you can take advantage of a more general situation. If you have done fluid mechanics, this is very commonly done. So in this case, supposing I take this entire set of equations, divide all the stress quantities by yield stress, the corresponding yield stress, and all the strain quantities by yield stress by epsilon, yield stress by E, then I'll get something like this. If you notice carefully here, the only parameter that arises from the elasticity is Poisson's ratio. Can you see it? And if the Poisson's ratio is 0, nothing of plastic deformation comes into picture over here. That's the beauty of non-dimensionalizing. When you write a code, it may be a good idea to non-dimensionalize and work on
Sir, can you
non-dimensionalized.
tell that again when Poisson's ratio is 0?
If Poisson's ratio is 0, you will find that it does not depend on any parameter that is associated with elasticity.
Okay.
All these quantities, the small e, p, tau, gamma, epsilon, p, all these are normalized quantities as per what is given over here. Just a way of doing things. Let's go to hardening. Any questions so far? It's a very simple addition of adding a spring to the model. If no questions, let me proceed.
Okay.
We had hardening that we specified in 1 dimension. Now, how do I specify hardening in 3 dimensions? Right? The way that I can introduce hardening is I can introduce a parameter called phi, which has to do with the determinant of K versus determinant of C. What is the value of phi if it is elastic?
Unity.
Unity. And what would be the value of phi if it is plastic deformation?
More than one.
More than one.
More than one? Look at this. It is I minus this.
Less than one.
It will be less than.
It will be always less, or in other words, there is a degradation that occurs. Yeah?
Yes, sir.
I use this word degradation so that you understand that there is this degradation which can be associated with damage. Okay? The rest of the things are exactly the same. We already know how to find out kappa. We also know, I'm just writing it as sigma dot y. The other way to write sigma dot y is what? Is what? How do I write sigma y dot? It is root 3 by 2 kappa dot.
Oh, yes.
Right?
Yeah,
So
lesson
that
between
it
sigma
is
y and
possible
kappa.
for me to write in this form. Kappa dot is equal to this, which is exactly the same thing that we did in lumped parameter.
Yes, sir.
Okay? Except that I need to be clear about how the translation has occurred from one dimension to three dimensions. For example, this same S would be nothing but root 3 by 2 of epsilon 11p. Similarly, kappa would be root of 2 by 3 sigma y. And if I plot this 2 by 3 sigma y versus root 3 by 2 epsilon 11p for a uniaxial, let's say, tension, I'll be able to find out how kappa varies with S. If this is clear to you, you know how to find out hardening of the material.
Sir, is it necessary that how the kappa varies means according to that only sigma y will be vary?
Yes, this sigma y relationship, sigma y is nothing but uniaxial tension yield. When I conduct an experiment in the uniaxial state, it will
Okay.
peak at sigma y.
So, sir, what is the need of implementing kappa over here?
Kappa is nothing but in the three dimensions we used kappa. Are you confused?
Sir, little bit actually sigma
Yes.
y and kappa
See,
means.
what happens is when I translate from a single dimension to multi-dimension, in single dimension, I directly used sigma y. But in three dimension, I had to remove the pressure component and only look at shear component in order to derive equations.
Okay.
That's the reason why this primary relationship between kappa and sigma y and the magnitude of epsilon p versus magnitude of uniaxial plastic strain coming into picture.
Okay, sir. Okay.
Nothing else.
Okay, sir.
So if I have to use the experimental plot of the uniaxial tension versus uniaxial strain, which is sigma y versus epsilon 11p, then I should do something like this, because each one of these represent the magnitude of epsilon p. There's nothing but S and kappa to get this relationship. The kappa versus S relationship is through this, so that I can find out this function. Is this clear?
Yes, sir.
So how do I find out this relationship? I find this out through an experiment. So far, so good?
Yes, sir.
Okay. Now I can introduce the hardening part also. And that's not very difficult. All that changes here is kappa, correct? This
Yes, sir.
K,
Yes, sir.
which was a constant earlier, is now kappa, which is varying. That is S dot is equal to phi times
K.
kappa. Is this clear to you? This comes from flow rule.
Yes, sir.
Yeah. Yeah.
Yes, sir.
Okay, and this is the hardening function that I can introduce. Kappa dot is equal to theta times S dot. Forget about this. This is for the example that we have solved in the book. For your case, you will draw the experimental plot and find out what could be that particular function. Okay.
Okay, sir.
Okay, sir.
The rest are all same. If you notice, all we need to find out is the relationship between sigma dot and epsilon dot. Correct? But
Sir.
in order to do that, I will have to use all these equations. This will yield a system of 14 equations with 14 unknowns. That is 6 stress quantities, 6 strain quantities, one value of S and one value of
And
kappa.
one LU, okay.
Yep.
Yes, sir.
Clear?
Yes, sir.
Yes, sir.
I'm saying kappa here, it can also be phi, left to you. So if I have simultaneous equations of 14 equations and 14 unknowns, it is possible for me to find out all these quantities as the loading continues. In a single dimension, we had only one quantity versus another quantity. In a single dimension, this was one value, this was one value, this was one value, and this was one value. So we had 4 equations, 4 unknowns.
Unknowns.
Here we have 14 equations and 14 unknowns.
14 unknowns.
And the same kind of code that you have done for one dimension can be used here in order to solve the problem. So far, okay?
Yes, sir.
Yes, sir.
Right? Now, I'll just stop sharing this one.
Sir,
Yeah, go ahead.
in this, there are 14 unknowns, right?
Yes.
So, sir, these 6 stress and 6 strain components only in case of isotropic case, right? If it is not isotropic, then the stress components could be 9, right?
Why?
Means if the stresses in the, other directions are different, then
Stresses are always symmetric.
No, those are
Strain is always
stresses, not
symmetric.
material.
Unless it's a polar medium.
okay, sir.
The way I define stress and use moment equilibrium, the way I define strain and how I define the shear components, automatically both stress and strain are symmetric.
Okay, sir.
Got it? Now,
Yes, sir.
Now, one more thing that I have not talked about. One more thing that I have not talked about is kinematic hardening. Yes?
Yes, sir.
Do you remember that?
Yes, sir.
Yes, sir.
Yes.
Okay. Now, I'm not going to cover that over here. But the kinematic component, if you remember, we used an alpha, right? We used something like sigma minus alpha goes to a critical value. You remember this yield condition
Yes, sir.
in one dimension, right? Absolute value of this minus k is equal to 0 is the yield condition, where this is the kinematic hardening parameter. Long time, so definitely you would have forgotten. This is that Boschinger spring.
Yeah.
Yes, sir.
It should be having
Remember, Boschinger spring was defined as alpha dot is equal to a function of plastic strain with some, let's just say, shall I call it as, give me some name, beta, okay? Where beta could be a function of the current stress and epsilon p. Okay. How do you now take it to 3 dimension? Give me a simple idea. This is a 1 dimension that we have written, where beta is nothing but the
function of that is
but
Function of
can be written as
in relation to washing a spring, this beta is
Beta is
just
spring
spring
constant.
stress in that spring is alpha,
alpha.
Beta is spring constant.
strain in that spring is epsilon, and therefore beta is
Spring constant.
Dot by
spring
epsilon.
constant of that Boschnger spring. In this case, if it is 3 dimension, how will I now change this to 3 dimensions? All I have to do is
epsilon
That's
dot
the
b
matrix.
should be
Equal to beta epsilon dot p matrix. This clear? This is a simple form that I can define. If this beta were a function of the current stress and plastic strain, then it becomes a nonlinear spring. I hope you're not confused so far.
No, sir.
It's a very simple extension of one-dimensional understanding. Okay,
Yes, sir.
yes, sir.
I'll wrap it up today, but if you have any questions, you can ask now, or we can have a separate session where you can ask questions. But I want you to digest
Sir,
what we have discussed.
sir, here alpha dot in 1D and 3D, the beta will be remain same in both the case, right? Only the alpha and epsilon p from
No,
1D
beta
to
is some spring constant in a 3-dimensional state of spring constant.
okay, means it is same in 1D and 3D also.
It's a constant that you can use, or it could be a function of. See, that's what I've written here. No, it could be a function
Okay, sir.
like this, or it could be a constant.
Okay, sir.
Correct?
Yes, sir.
In the notes, we have solved one for an aluminum bar. Right? I want you to go through that. See if you can simulate the response given in the book.
In
MATLAB, using MATLAB.
okay, sir.
My request is first, do not see the MATLAB code that we have used. You generate by yourself. Get the confidence
Okay,
that you can do. Then you can have a look at how we have written the code.
okay, sir.
Okay.